Hello everyone, and welcome to the first chapter of a new video series called Code With Me. I'm Jackson, and I'm a computer science student at Washington University in St. Louis. This video series will focus on bringing you all with me to build a project that I currently find interesting in. I'll bring you guys all along for the building and learning process, and hopefully throughout that we'll both learn something together. So the first project that we'll be building in this chapter is Campus. So this project will essentially be Club Penguin minus the penguins, and we'll be using capybaras instead. And what will also change is the map. In Club Penguin, the map is pretty much static with a few changes that we have. However, this app, the map will be based on the college that you go to. This will create a sense of familiarity with people to actually meet each other. And the reason why we're using capybaras is that many college campuses do not use capybaras, so it'll be create an unbiased sense. And I think a lot of people do like capybaras, so I think it'll create an enjoyable experience for people. So the reason why I want to build Campus is that I want to create an online world for college students who may struggle to make new friends in an in-person college environment, a virtual means to do so. Loneliness is a pretty known epidemic in the modern century, and I think this would be a fun way to meet new people who go to the same college as you, or maybe just meet someone you would never meet in person. But what I really want to focus on in this project is creating a distributed backend where multiple servers can represent one game instance. The reason why this is important is because Campus is meant to host a college population. And the worst case is that everyone in the college joins, which again is unlikely but could happen. So that would imply that 4,000 people would be on the same computer at the same time, which would be a big problem for just one computer. And one option is to vertically scale, in which you just keep getting beefier and beefier machines. The problem with this is that this is really expensive. So an alternative solution that I want to tackle is creating a horizontal scaling solution in which I can just add more computers, and these computers will be able to share one game instance and allow for 4,000 people to have a seamless experience. So the next part of this video will focus on diving into the tech stack and the system architecture that we'll be using for Campus. It'll cover mainly the components we need to build, the languages and frameworks we'll be using, and also just how the project will actually work. I'll try to keep it brief for the sake of time, but I think it'd be helpful for both of us to understand what we're actually building. So I'll cut to that, and I'll see you there. Campus will be comprised of three main parts: the game client, the authoritative server, and the fleet server. The first part of this project will be the Phaser game client. Phaser is a JavaScript framework that allows us to build the front-end component of this game, such as sprites moving around and displaying visuals. The game client's main job is to simply be cute, allow players to send inputs to the fleet server, and represent the backend game state. The authoritative server, for now, will be a straightforward Node.js web server, as it will also be easy to implement with Express and has a lot of powerful libraries that play nice with serving web content. In the future, we may upgrade this to a quicker, more serious framework, but for now this will do. This server's main job will be to handle web content delivery, user authentication with a Postgres database, and fleet server management with a cache database using something like Redis or something else. The last part is the fleet server. The fleet server will be a WebSocket server written in Go. The server's main job is to handle backend game logic, manage players currently connected to it and the game instance, and to simply be fast. The fleet server will also need to communicate with the authoritative server to communicate its state, such as it's on, it's off, full, etc. For a little in-depth how multiplayer games work, the game that you download is simply just a cute representation of the current game state, which in reality, the real game and its logic is done on the backend. For our example, we'll have a little sprite representing what the player sees, while on the backend, it's just data. Then when a player, for example, inputs W, we send that input to the backend and update its state. Then we send that new updated state back to the client, and then the client will render that to show the penguin moving. To hammer in the point, I'll run through a quick demonstration of how the project would handle a user joining the game. First, the user and the authoritative server would connect and communicate utilizing a CRUD API. Then, when the user connects to our server, the client will ask for our website, in which we'll return the HTML code for them to render on their web browser. Then, the user will need to log in, and we'll reference that with our SQL database and return a token if they are successful. Then, when the player wants to join a game, the Node.js server will use a cache database, such as Redis, to check which server will be appropriate for the client to join. This will usually involve checking which server has the least amount of people, and will act as a load balancer so we can evenly distribute players and not bog one server down. Then the authoritative server will send the server's information back to the game client, and they will establish a WebSocket connection. Then the player can send user input to interact with the game, in which the fleet server will then update the current game state. If, for example, another player joins the game, assuming it's already connected, When our original user inputs a button, the Fleet server will update both clients at the same time to represent the new game state. Similar to like if you move, your friend will see you move on their end. The game server updated both game instances at the same time. So that's a brief rundown of how this project will work and be architectured. There are different edge cases that we do need to handle, and we also need to be able to distribute one game instance among multiple Fleet servers, which in all honesty, I have no idea how to do. But again, that's something what I want to learn from this project. So now, the next part of this video will go actually into coding a basic WebSocket server. We won't do too much since this is the first video. Essentially, we'll just create a basic web server that can serve basic HTML content since we don't have the web server created yet. And then we'll be able to create a WebSocket connection. And I'll showcase my entire process throughout that. So I'll see you there. So right now I have a basic Go project set up with a client folder, a CMD folder, and an internal folder. Next, what we'll do is just start creating the source files for our CMD and internal folders. And then we can start with main.go, and then we start creating the server Go, and then we can create the routes that will add the routes to our WebSocket server for a connection to happen. The next thing I'm going to work on is server.go. First, I'm going to create a package, and this package would be server. Then I'm going to import GIN, which is a basic web server library, and I'm going to create a function, create server. This function will allow us to basically create a web server and spin it up and allow other functions to call it. Then I'm going to start the router with gin.default, which creates a web server with basic settings. Then I'll do router.run, which will start the web server on port 3000. Then I'm going to create a comment here that's going to just remind me to call a function that will add routes to our web server. Next, we'll create the function to actually add the routes. So first, we'll go into routes.go, then do package routes, import gin again. Then I'm going to create a function create router, which takes in a gin.engine, which indicates our web server. Then I'm going to create a map that basically maps a string, which is going to be our route, to a callback function, which takes in a GIN context, which is basically just the package that's being sent and the response object. Then I'm going to pass in the landing route and then a landing callback function, which we'll define later. Then I'm going to create a for loop that goes through each key and value pair and creates a get route for the route and the callback we define. Then I'm going to go into callbacks.go, make it under the same routes, and then I'm going to create a function landing, which takes in the GIN context, and it's going to return an HTML file. And it's going to give it a status code 200. This is the index name, going to be index.html, and then just empty headers for now. The last thing for our route package is we're going to create our WebSocket function. So we'll create another package under routes. Then we'll import FMT, which allows us to print to the console. We're going to install GIN again, and then Gorilla WebSocket, which we'll use to upgrade a route to a WebSocket route. Then we'll define the upgrader, which is essentially just saying how many bytes we're going to take in a read and write, which will just do 1024 bytes just for a safe number. Then the next thing we're going to do is create WebSocket function, which takes in another GIN context similar to a normal route. Then we're going to upgrade the C writer and the C request to a WebSocket connection, which will then return us a connection object and an error object. If the error exists, then we're going to print to the console that something went wrong and return early from the WebSocket. The next thing we're going to do is defer the closing of the connection, which is essentially just saying once the function ends, we'll close the connection. Then we'll write our message with con.writeMessage, which we're saying is going to be a text message, and then we're going to turn our string into a byte array that we send over the internet. Then we'll create a route in our getRoutes map for WS for WebSocket, and then we'll pass in the create WebSocket function. Then lastly, once we're done with that, we're going to call our create routes function in our server.go. And then last thing we're going to do is just add some HTML and static functions that allow us to actually send HTML code and our static objects over the internet. Next we're going to do is we're going to go into the client and create our pages and static folders. Then in our pages folder, we're going to create a landing.html that we defined earlier in our route. Next thing we'll do is create a super simple HTML template using VS Code's inbuilt one, do a Capy start title, and create a nice little header tag that just says hello so you can see that our web page actually renders. The next thing we'll do is actually write the JavaScript code to connect to our WebSocket server. In the future, this will actually be actually good. For now, we'll just have this, just make sure that we can actually establish a connection. Then we'll create callback functions so whenever we open a WebSocket, we'll print hello or it's okay. Then when we receive a message, we'll print what the message we get. On close, we'll just say that the socket closed. This would be just to see that we actually did make a WebSocket connection and receive the message that we sent. The last thing we need to do is actually create our main function. So we'll go into main, create a package main, a function main. This would be the first function that actually runs when we run our server. We'll then import server and then just run server.createServer, which will start our web server. Then we go into the console and actually install all the packages we were naming with go mod tidy, which all the red lines go away. Then we'll run our server with go run cmd, and then main.go. Then we should see nicely that a web server pops up in our terminal, and boom, we have a nice web server up. To see that it's a WebSocket server, let's go to the actual URL, and you can check the console. And now we can see that we actually received our WebSocket packets, and see that we actually have a WebSocket server up and running. In the next few videos, we'll be building on our basic WebSocket server that we've made to actually implement game mechanics, and I'll start working on a basic phaser client that allows us to actually have sprites move around. And then what we'll try and do is get basic movement mechanics to work, to where we have two web browsers open, connected to the same server. When I move one of my capybaras here, the other person sees it and actually looks like a multiplayer game. So I hope you guys really enjoyed this video, and I'll be trying to make these videos every 2 weeks, but we'll see if school gets in the way with that. And I'll also try to make some other videos that are like hands-on tutorials, like create this app with me. It'll be fun. So please leave comments. I would love to hear feedback, and if you enjoyed this video, leave a like. But again, have an amazing day, and I'll see you guys in the next video. Bye bye.